Okay, now we're going to look at the Townsend principle, in which this is among the fundamental experimental work that been done conducted by the Townsend to describe the phenomena involved in the breakdown in the gases. Okay, for example, the ionization process, the ionization collision in the gas, the ionization collision on the cathode, which is the electrode, and the photoionization phenomena within the gas dielectric materials. These three principles, as what I just explained in the previous topic about the ionization phenomena. Okay, we look some basic terminology for this one, since it is experimental work. Anode, as we know, is a positive, cathode is negative polarity, positively charged, move toward cathode, obviously, negatively charged, move toward anode. They are attracted toward the opposite charge. And then the breakdown voltage, we call it VB, voltage breakdown, V for voltage, B for breakdown, in volt or kilovolt. And breakdown electric field, we call it as EB. E is electric field, B is breakdown. And the unit is in volt per centimeter, or we can also say in the kilovolt per centimeter or kilovolt per meter. Alright. Okay, I don't want to talk about this. I will explain this later. Okay, these are the experimental setup conducted by the Townsend. Townsend, our scientist, has developed this experimental work to describe or to further understand about the ionization process in the gas. Okay, he want to know the how and what is the causes or the influence of the ionization in the gases that lead to the total breakdown. Okay, he set up the experimental work in which they have two parallel electrode here. Okay, parallel electrode within a chamber. Okay, the chamber, because he want to fill in the chamber with the gas. Okay, and he bombard this electrode with a UV light. Okay, UV light. So bombard this electrode. Okay, and this circuit is connected to the external potential, in which we can vary the potential to apply the voltage, the potential difference between these two electrodes, and we have the electrometer to measure the voltage and current. Okay, this is the simple experimental setup by the Townsend. We have the voltage meter, we have the ammeter, voltmeter, and we have a chamber filled with the gas, and within the chamber we have the parallel plate. Why we use the parallel plate is because we're going to produce a uniform electric field within this region. Okay, we're going to produce a uniform electric field within this region. Okay, from this experiment and from the measurement data, he plot, for example, current versus voltage, and it turned out to be this shape. Okay, this shape. So the current versus voltage, and he already described this into several regions, and which this will be explained later. Okay, I don't repeat the procedure, the test method you can read by yourself. It's just what I explained here. Okay, the Townsend process. Okay, the Townsend process. Okay, he obtained what I would like to highlight here is the alpha and the gamma. Okay, Townsend first coefficient known as alpha, and the Townsend second coefficient known as gamma. Okay, He developed this coefficient based on the experimental work, in which the alpha is the average number ionization collision made by one electron per unit drift in the direction of electric field. Okay, this is referred to region 3. Okay, and the gamma coefficients, the Townsend second coefficient, or represented by this gamma, is the average number of secondary electron produced at the cathode per ionizing collisions, okay, in the region 4. Because the alpha is the first Townsend coefficient, and the gamma is the second Townsend coefficient. First is and the current, okay, the current from the Townsend experiment can be expressed into this expression, which will be explained later. Okay, this is the current voltage curve that been plotted by Townsend, and he already categorized into 4 region, 1, 2, 3, 4, and he already categorized V1 as at the region this one, V2, V3, V4, and he also categorized as I note as the saturation current here. Okay, what actually happened during the experiment? Okay, this simple illustration should help us to understand what actually happened and how the Townsend tried to validate the photoionization, the ionization of cathode, and the breakdown that occurred within the gases. Okay, like this one in the first stage. Okay, this one actually, if you can see clearly, this one is the representation of the photo chamber, and we have the parallel plate. Okay, this chamber is represented by this one. Sorry, let me just check this one. Okay, this one. Okay, this chamber. Okay, we have anode and cathode. Obviously, two parallel plate to provide a uniform electric field, and anode cathode. So the electric field will be developed between these two electrodes. And since we are okay, if you can see here, we have UV radiations. Okay, photoelectron travel towards anode. Okay, the UV radiation bombard the cathode like this one. Okay, UV radiation bombard the cathode. Okay, when it's bombard the cathode, enough energy, as I explained previously in the first ionization process, this will transfer a certain amount of energy into the electrode, in which the electron should have sufficient energy to escape away from this cathode. Okay, once it's escaped away within this gas chamber, it will just attracted to this anode. Okay, because it is negatively charged, so it will be attracted to the anode. Okay, this is the first stage. What happened when you bombard the UV light? Okay, this is represented by region 1. Okay, where is region 1? This is the region 1. Okay, the region 1 in which we can see the current start to increase almost linearly. Okay, almost linearly with the increase of the voltage. Okay, so we increase the voltage. Okay, we have the voltage, external voltage that we increase potential difference between this one, and then more and more electron will escape from the cathode to drift through the anode electrode. Okay, this is the first region. Okay, and then we come to the second stage, in which the anode, okay, we have photoelectron rich anode, region 3. Okay, if you can see, it is region 3. Region 3 is, so sorry, this is region 2. Sorry, that is, the letter is very small. It is region 2. So it is region 2 in which the increase in the voltage will cause no increment in the current. We have the voltage in the region 1, the increase of voltage cause a increment almost linear to the current. And then we come to the saturation level in which the increase in the voltage doesn't cause an increase in the current. How to describe this region 2? Okay, let's see this one. Okay, once this one, all the electron reach the anode, okay, that is when the increment of current will not happen, because all the electron already settle at the anode electrode. Okay, so photoelectron reach anode. Okay, they stabilize at this region, and that's why the increment in the voltage doesn't increase the current flow. Why? Because all the current all the electron is already here. There is no further electron from the cathode. Okay, let's see what happened next. Okay, what's happened next? Ionization by collision in the gas gap. Okay, what happened during the movement of this electron to from the cathode to anode? This one will somehow cause a collision within the material, within the gas here. Means that we have positive and negatively charged, and then they are moved toward each other. The negative going to anode, while the positive charge is moving to the cathode. The movement of this one will cause the collision within this one. That's why it trigger more and more ionization process that increase the, what we call it, the current here. We apply the external voltage, we increase from V2, say for example, to V3, and then there will be an increment to the voltage due to the ionization by collision within the gas gap. Okay, and finally, what happened is that the satisfaction condition to the breakdown in the gap. What happened once all the negatively charged particle at the anode and all the positively charged at the cathode, this is between the gap. This is what we call or classify as a total breakdown, in which, in this case, for this case, the increment in the UV light will not will not cause a further increment of the current. The current will rise steeply and will rise. Okay, the increment small voltage level will cause almost infinite current, in which this is in this state the dielectric material will become a conductor. Okay, this representation explain the phenomena, explain what is actually going on at this 4 region. Okay, I don't need to repeat and to explain again. Okay, so you can read by yourself. What most important here, what we want to know is, during the region 1, the photoionization process occurred from the UV radiations to the cathode, in which will release the electron into the, and the electron move to the cathode. Okay, and then next, region 2 summary, we have the saturated photoionization process, in which all the electrons settle at the cathode, and then addition of so the addition of voltage level will not cause an increase in the in the current, and this will give the saturation current, and referred as I note, which is saturation current is equivalent to the electron and number of electron, charge of electron times the number of electron at the saturation level. Okay, And in this case, obviously, the electron is represented by electron charge is equivalent to 1.6 times 10 to the minus of 19 coulomb, right? Okay, no charge particle produced by the ionization gap, because no ionization, no current, no increment in current. Okay, and the last, the region 3, this is the region where in which we classify as the ionization by collisions. As I explained before, the movement of positive or negatively charged toward the cathode and anode will cause a collision between the molecules, and that will promote further ionization process, and hence the acceleration within the molecule, the kinetic energy will further increase the electron for the probability of the ionization process. Okay, the kinetic energy between the collisions, like I explained before, will cause the probability of the ionization process to increase. Okay, in this case, for simplicity, for a good understanding, the ionization means current conduction. Okay, as simple as that. Ionization means the initiation of current conduction. The more the ionization process, the more the current flow will passing through. Okay, even though we know that ionization process is the transformation from the molecule or atom from a stable molecule into the positive or negatively charged, right? And region 4, okay, region 4 is sustainable ionization process. Okay, sustainable ionization process, or what we call it as independent ionization process. Okay, why we call it as a sustainable ionization process? Why we call it as a sustainable, or why we call it as independent? Because in this region, the ionization process is actually occurred. Okay, and it is sustainable, in which we cannot control the ionization process, and it happened by themselves. By looking at the current, we call it as a total breakdown, or current flow will passing through indefinitely. Okay, and in this case, what happened, if we translate into the problem with the dielectric material, it refers as total breakdown of that material. So in this case, the dielectric material will become, from the insulator state, will become a conductor. Means that the material no longer function as the insulator, so it's become conductor now. That's why we call it as sustainable. So it means that the ionization process not require any external factor to progress in the ionization, or in the current flow. So we cannot control, and even though we remove the external factor like UV radiation, again we cannot control, and it's become independent and sustainable. That is what we call as total breakdown. Okay, Townsend electron avalanche. Okay, analysis for region 3. Okay, we go specific a little bit extra detail for region 3. We call it electron avalanche. Okay, for the electron avalanche in region 3, okay, by looking at this figure, okay, for example, electron multiplication called electron avalanche. Why we call it avalanche? Okay, if you for people who in sport, avalanche is referred to the drop of a sudden and a massive drop, or massive change in one state, from one state to another state. Or in this case, okay, electron multiplication. Why we call it as multiplications? Because of the ionization by collision within this gap, the gas. Okay, This refer to region 3, and we call it avalanche because it happened massively. And during this, one electron avalanche will cause multiple electron collisions. One will collide, will produce 2, 2 will produce 4, 4 will produce 6, 8 will produce 16, and so on. It like a progressive geometric. So that's why we call it avalanche. And this happen, that's why if really we relate to this point, it's happened here and it's increased exponentially. Exponentially. But still within this region, we still manage to control. But once it's come to the total breakdown, that one is, we call it as a total failure. Okay. Okay, as for the region 4, further explanation on this region 4. Okay, as what we know in the region 4, the Townsend suggests three secondary principal process that affect the current in addition of the primary discussed alpha that occurred in the region 3. What does it mean? What does it mean? Further ionization, the secondary ionization process that cause the current will maintain to increase in region 4 even though UV light source is removed. What happened here, the positive liberated avalanche will cause ionization by collision while moving from cathode to from anode to cathode and cathode to anode. This excited atom avalanche will emit obviously photon or electron to return to its this original state, to the normal state, and this photon may cause a photoionization. Photoionization, which means we don't really need the external photoionization process triggered by UV light. So it kind of self-made process, or this process, as what I mentioned before, is we call it as a sustainable breakdown, sustainable ionization due to the presence of the photon and electron within the gap. So in this case, if we remove the UV light, nothing will happen. The ionization will continue until the current will increase exponentially or indefinitely. I will continue about the alpha, about the primary coefficient, Townsend primary coefficient, and beta, the Townsend secondary coefficients, in the next video, inshallah.